about AI-driven digital twins for predictive maintenance. That's today's agenda. So the background to this is that operations and maintenance of facilities is the longest and most resource-consuming phase of the building. Some say it costs 70 to 80% of the total life cycle cost of the building is in operations and maintenance. Effective facilities management ensures that buildings are functionally safe, comfortable, and efficient for the users. The key challenges we face in modern FM include balancing complex operations, overcoming organization silos, adopting new technologies, and addressing skill gaps. So this is the building, it's a building on the campus of the University of Florida that we are using for this example case study. So currently what we did is we took the building information model and used Autodesk Tandem and created a digital twin, and that was the status twin. And our goal is to go from a status twin to an AI-driven digital twin or even a cognitive twin. So the issues in machine learning ready digital twin infrastructures are the continuous integration of all the building data streams, automated ETL standardization, open AIs and extensibility. There's a lot of telemetric streams that we have to integrate and match. And the predictive edge of this is we can get, with the energy system we're using here, next day key performance indicators, detect faults, activate actuators, and optimize the scheduling. So it's able, instead of doing maintenance once a quarter, using a digital twin system, we can do maintenance every day. We can observe the operations every day, or every hour, or every minute if we want to. So it's continuous O&M. So the research gap, as we see it, is implementation, interoperability between computerized facilities management and BIM. They're both in data silos, and we need to seamlessly integrate this. There's a lack of standardized workflows. Everybody has their own process. The scalability, current research, as we noticed earlier today, is based on single buildings. Our goal is to have a campus-wide system where this really is effective in, when you're looking at hundreds of buildings and energy savings and energy consumptions and predicting the consumption. And all this also is impacted by the difficulty in scaling up the solutions. We're using advanced analytics here as well as machine learning. So the case study, we developed a live digital twin and deployed it for operations and maintenance. Embedded in it, there was a machine learning process, and the building we looked at was a 3-story academic facility. It had existing digital infrastructure, building automation system, workplace management system, BIM, and there was active collaboration with the campus facility services and IT departments. So this is our technology stack, Autodesk Tandem, the data sources, API, the ETL, ML, using Python, Keras, and Pandas. These are the layers we're integrated. You can see the integrated workplace management system, the building automation system, the document management system, the asset management system. All of those were integrated in the digital twin. And here is the data population that was fed into the building. The components of the software system were the asset works, the Siemens and Johnson control systems, loops, the Meridian document management system, SkySpark, emergency management. All that data was integrated in the common data environment at Tandem and displayed on the digital twin. From an owner's perspective, they're getting high-level performance matrix, cost insights. They can use it for strategic planning. When facilities managers and maintenance team, they are looking at real-time operational data, fast incident tracking and resolution, and they're alerted when there are critical equipment failures, and the occupants, of course, are given their comfort space availability, and so you can schedule rooms, you can schedule classes and things like that. So this is the digital twin deployment. On the left-hand side, you see a heat map of the temperature in the building. On the right-hand side, you see room usage, space usage in the building. This is the machine learning integration in the process. So we're looking at the sensor data, the meter data, the equipment space. You see the transformation from the physical asset to the digital twin. We have the predictions. So what we have here is we get daily weather data, and of course you can get a 7-day forecast or a 10-day forecast. And in this process, we can define the window. We want to look at 1 day at a time. We want to look at 3 days. We want to look at 5 days, 7 days, 10 days, and then we use, we have about 8 years worth of energy data. The building is 8 years old, and we're using that to train our machine learning system, the neural network, to help us predict energy consumption for the next day. And once we predict and validate that, that becomes part of the data, and we predict the future. So if we look at this, ingest is historic data and live feeds from the sensors, meters, and weather. We align the timestamps of all of these and aggregate it. Then the learning process, there's contextual data. We feed in there the holidays, the operating schedule, because on holidays, of course, energy consumption is low. And then we have the rolling window sequence that looks at so many days ahead. The model selection and tuning, we use the long short-term memory algorithm, and we use neurons and dropouts. And what we published was we get the weather forecast, generate new predictions using this trained model, and post via the API pipeline to the digital twin the predicted consumption. And then we auto-retrain when the mean error reaches a certain level. So these are the performance insights. You can see the model captures short-term dependencies and seasonal shifts in energy consumption. And the model tuning, here's the sliding window on the right-hand side. Dropout equal to 0, and dropout is equal to 0.3. And then we publish all this data, so you can see energy consumption day 0, day 1, day 2, day 3. So if you had a solar array feeding the building, then you can determine how much energy you have to purchase from the grid to meet your demands, for example. Outcomes and recommendations. The outcome is we deploy a full-scale DT for operations. We prove the feasibility of machine learning embedded in the live digital twin. We automate end-to-end data pipelines with extensible architecture. The limitations are we only looked at one building, of course. There's no user evaluation, and this is single model scope for forecasting. Our goal, of course, to have the whole campus forecast. The recommendations is to implement active alerting, expand on the machine learning use cases to determine equipment fault detection, and expand data sources incorporating multiple facilities. Questions? I know that was fast, but.